Hi everyone, I'm DUTHEIL from Avignon, and today I'm going to talk to you about the impact of non-starch polysaccharides on the textural behavior of processed yam. This research is part of the RTBfoods project that is focused on different components of the West African diet, such as cassava and yam. Its goal is to team up with farmers, food industries, and consumers to define key quality traits for the development of new adequate cultivars for everyone. Why did we choose to focus on cell wall polysaccharides? Well, there has already been some investigation on the impact of starch content, dry matter, and amylose on textural properties of starchy food. It explains partly the texture, but it doesn't explain it all. Moreover, in potatoes, a correlation has been found between pectin metylesterase and the texture of cooked potatoes. Pectin metylesterase is an enzyme which acts specifically on pectin. In Avignon, we researched the impact of non-starch polysaccharides on the texture of apples, and we found an impact both in raw and cooked apples. During cooking processes, some polysaccharides stay nearly the same. It's the case of hemicellulose and cellulose, and some can be transformed by the cooking process. This is the case of pectin. So what can happen? Well, there is two enzymes first that can act on pectin during cooking processes. Pectin metylesterase, which acts on methylated pectin, which will demethylate it and lead to gel formation in the presence of calcium. Polygalacturonase acts on non-methylated pectin and cuts it, which leads to viscosity loss. There can also be chemical reactions such as beta elimination. Our objectives are the following. We want to map out the composition of yam non-starch polysaccharides, cellulose, hemicellulose, pectin, and when there is some, mucilage. We will research the impact of these polysaccharides on the cooking behavior of yam, and we'll try to understand the mechanisms involved. Our general approach is to work with well-characterized and controlled sources of yams with contrasted properties in terms of cooking behavior. Then we extract the cell walls, because it is in the cell walls that we will find these non-starch polysaccharides, and we will do so on raw and cooked products. And once they are extracted, we analyze them. Our yams come from Guadeloupe. We worked on two different species, Dioscorea alata and Dioscorea esculenta, and 5 varieties in total. For Dioscorea alata, we had the opportunity to harvest tubers from two different sites. Godet is a site which is low in altitude, has a calcium-rich soil, and a moderate rain. DUTHEIL is a site with a rainy climate and a higher altitude. As said before, we worked on raw and cooked samples, so all cooked samples were steamed for 20 minutes. To analyze all yam non-starch polysaccharides, we needed to extract them, because starch is a polysaccharide, and if we just look at the polysaccharides in our yam dry matter, we will only see starch with our method. So we developed an enzymatic starch removal process, which has to be done on alcohol-insoluble solids, because in alcohol-insoluble solids we removed the polyphenols, and polyphenols can inhibit the whole process. So this is our extraction method. It relies on the action of alpha-amylase and amyloglucosidase to transform the starch in glucose, and then we added subtilisin A which is a protease to remove the remaining enzymes. Here are the analyses we made. So on fresh yams, this was done in Ray Guadeloupe. There was a measure of the cooking time, of the water intake, and of the texture. In Ray Avignon, we assessed the enzyme activity. On alcohol-insoluble solids, we measured the starch content, and then on starch-free AIS, we looked at the polysaccharide composition of the cell wall. So we measured the remaining starch to be sure to take it out and not consider it as cellulose or hemicellulose, for instance. And then we measured the content in neutral sugar, methanol, and galacturonic acid. So these are the main characteristics of raw yam. Firstly, there is a low galacturonic acid content. It is lower than in cassava and in potato. All findings are consistent with the values found by Christian Mestre in CIRAD, who also works on yam. So this is not an artifact due to our analysis method. This is quite reliable. Yam also has a low to medium methylation degree, so in raw yam we found 37 to 58% methylation of our pectin, and it tends to decrease when we look at steamed yam. It's a little bit lower. The pectin of raw yams are quite highly branched. So here you have a scheme of what pectins are made of, chemically speaking. So pectin are characterized by a galacturonic acid backbone, and then there are branches, and most of these branches, they start by a rhamnose, which is on the backbone, and then you have galactose and rhamnose. This is a rhamnogalacturonan 1. So we look at the ratio between galacturonic acid, so the backbone, and the sum of rhamnose, arabinose, galactose, which is the branches, and we see that this ratio is quite low, meaning that there are more sugars in the branches than in the backbone. Moreover, yam is rich in galactose. It's richer in galactose than cassava, but it's quite in the same range as potato. So when we look at the rhamnogalacturonan branches, we see that there is more galactose than arabinose in them. We looked at the differences between Dioscorea alata and Dioscorea esculenta in raw samples, and what we saw is that Dioscorea esculenta has higher mannose content than Dioscorea alata. Mannose is not really a sugar which is characteristic of pectin, so we had to look at where it can come from, and in the literature there are data about the presence of glucomannan in Dioscorea esculenta, and especially in the mucilage of Dioscorea esculenta. So we looked at the mannose-glucose ratio in our samples, and you can see that in Dioscorea esculenta samples, this ratio is really higher than in Dioscorea alata samples, which is consistent with glucomannans. About the impact of the soil. So we had our 3 varieties of Dioscorea alata and our 2 soils. And what we saw is that the methylation degree of tubers harvested in Godet, the calcium-rich soil, is lower. It is really interesting because we know that low methylated pectin can interact with calcium to lead to gel formation. So this is for the raw samples. What happened then when we cook them? Well, this is the scheme I showed to you earlier, and we needed to revise it because when we looked at enzymatic activity, we did not find any pectin methylesterase activity at all in our yam collection. This means that there cannot be any demethylation due to enzymatic reactions during cooking processes. But there is polygalacturonase, so there can be some viscosity loss due to its activity, and there can be interaction with calcium. We saw 3 different cooking behavior. Firstly, we have the Dioscorea alata, Pacala, and Sinoa. For them, methylation degree decreased, as well as the galacturonic acid rhamnose ratio. This would be consistent with some beta elimination of methylated pectins and also with acid hydrolysis of rhamnogalacturonan and homogalacturonan. For Dioscorea alata cabusa, however, methylation degree increased. So this means that low methylated pectin were more affected by the cooking than highly methylated one. This could be due to the polygalacturonase, which acts specifically on non-methylated pectin. Indeed, we found twice as much polygalacturonase activity in cabusa than in Pacala. Finally, there is the Dioscorea esculenta. For them, during the cooking processes, methylation degree decreased, but the mannose glucose ratio increased. So, methylation degree decreases, it could be also some kind of beta elimination, but this mannose glucose ratio increases only for the esculenta, which shows a stability of the glucomannanes, which are from the mucilage. About the impact of the soil. We saw that tubers from Godet were firmer when in steam samples, which could be explained by the fact that there is more calcium, so more lead gel formation, so an improvement in texture. But it's not that good because for Pacala and Sinoa, tubers from Godet are also harder to cook. They take longer to cook. And as said before, we had this methylation degree of raw tubers harvested in Godet, which was lower. So what happens if we try to correlate methylation degree and cooking time? Well, we can see that there is indeed a decrease in methylation degree when there is an increase of cooking time. How can we explain that? Well, low methylated pectin are more prone to calcium complexation, and we know that in Godet soil there is a lot of calcium. So here we could see an impact of the complexation with calcium ions on the cooking behavior. In Dioscorea esculenta we had only 2 varieties, but we saw the same correlation. We also had a lower methylation degree associated with a longer cooking time. To sum up, we determined the chemical signature of Yam non-starch polysaccharides and especially of Yam pectin, which have a high degree of branching, medium to low methylation degree, and are rich in galactose. We saw differences between the 2 species of Yam, differences which are explained by the presence of glucomannan, which is specific to Dioscorea esculenta. Different mechanisms occur during cooking. Even though there is no pectin metylesterase in any of our samples, there are still differences in their cooking behavior. Finally, we saw an impact of the soil on the cooking behavior of Dioscorea alata, which is really interesting because calcium-rich soil seems to be associated with lower methylation degree and longer cooking time. And longer cooking time is not what we want when we develop a new variety. To measure methylation degree, here we measured the galacturonic acid content and the methanol content, and we used a ratio. However, there can be quicker method to estimate methylation degree, such as infrared spectroscopy, which could be used to measure the methylation degree and have an idea maybe of what varieties could cook quicker inside the same species. I want to thank the Bill and Melinda Gates Foundation, which is at the basis of this project, but also our colleagues in Guadeloupe, so Dominique Rinaldo and all the other one, because without them we would not have any samples. And finally, the quality and processing team, so here in Avignon, because it's here that we do this research. Thanks a lot for your attention.